Hello everyone. Today we are going to discuss the solution of fourth problem of Leetcode Weekly Contest 400, which is find subarray with bitwise and closest to k. So you are given an array nums and an integer k. You need to find a subarray of nums such that the absolute difference between k and the bitwise end of the all the subarray elements is as small as possible. So we have to find any subarray whose bitwise end is closest to k. Okay, now let's take one example: 1 2 4 5 and k equals to 3. Okay, so let's take this example. Say 1 2 4 5. What are the subarrays? Subarrays could be, there could be n into n minus 1 by 2 subarrays. So one subarray is taking the single elements. So thus if we take the single elements, the subarray are nothing but 1 2 4 and 5. If we take two elements, then it would be 1 and 2. 1 and 2 is nothing but 0, and then it would be 2 and 4, it is again 0, and 4 and 5 it is again 4 and 5 is 4. Okay, so 4 and 5 is 4, and if we take three elements, then it will be 1 2 and 4, it is 0, 2 4 and 5 is also 0, and if we take four elements, it is also 0. So we can take this element only single subarray this, or you can take the 4 and 5 this subarray. The answer is closest to k. So the difference, so the output is 1. 3 minus k is 3, and the closest we can get is 4, so the difference is 1. So similarly you can take the other examples also. Now let's jump into the possible solutions approach. Okay, so before going to that, let's discuss the observations or brute force approach. Of the brute force approach is obviously order of n square. Order of n square, it means that we will iterate over all the possible subarrays, and while iterating over the subarrays, we will try to find the bitwise end of the subarray, and we'll take the difference as the absolute difference between the current value and k. Okay, so the solution, brute force solution, is order of n square. Now let's look at the constants, and I don't think it will be possible. Uh, uh, the constants on n is 10 to the power 5, so it is not possible to solve using this brute force approach, obviously. Now let's discuss about some properties of bitwise AND. So let's say the bitwise AND, let's say of a L to R, should be always greater than equals to a of L to R plus 1. This is the property we'll need. Okay, now why? Because this thing, a of L to R plus 1, a of L to R plus 1 is nothing but a L to R and R plus 1 and a R plus 1. Okay, I hope you get it. Now, when we are doing bitwise AND of two elements, we always know that the bitwise AND of two elements is always less than equals to the minimum element. Okay, we all know that. So that's why we can say that this property holds. When we say that this property holds, that means for a given index I, okay, for a given index I, we can try binary searching for the values such that I to j is closest to k. Okay, so what I am trying to say is that, let's say bitwise AND of I to j is greater than k. Okay, greater than k. That means let's say if we take I to anything, I to, let's say p, such that p is greater than j, then this thing I to p, it should be always greater than k. So to check which element is close to k, we have to decrease the value of j. Okay, similarly, if we try to find, let's say I to j is less than k, then we can say, let's say I to r is less than k. Sorry, I to j is less than k, right? Then I to r, then I to r should be always greater than k. So if it is less than k, then we will go to the left side, and if it is greater than k, sorry, if it is okay, if it is greater than k, we will go to the right side, because the part right part will be lesser, and if it is less than k, we will go to left side, because left part will be greater. Okay, I hope to get it. I think I have missed something here, that if I to j is greater than k and I to p is greater than k, but I to p is less than I to j, right? I to p is less than I to j. So I to j, right? So we will go to this I to p range. So I will now jump into my code. My solution is something like order of n into 30 into log n kind of, and it is this time complexity is acceptable. Now I first will explain you the binary search approach, and then I will explain you how we are finding the bitwise AND in a range in order of 30 time complexity. Okay, now let's jump into the code. So here, let's ignore this part now. Let's ignore this part now. Let's delete this. Now, what we are trying to say is that for we will start from the ith index. Okay, right? And our right value is n minus 1. Now we are checking that what is the bitwise end from I to mid. We'll check what is the bitwise end from I to mid. Now that is inside our val. Okay, that is inside our val. Now if val is greater than k, now we are taking that difference is minimum of difference and absolute difference between k minus val. Now if val is greater than k, we will go to the right side, right? That's why we are doing L equals to mid plus 1. Yeah, otherwise we are going to the left side. I hope you get it, that the bitwise end is always decreasing in the right side. That's why when we are it is greater than k, the value, then we will go to the right side, and it is decreasing in the left side. That's why when we the value is less than k, we are going to the left side. I hope you get it. Now comes interesting part, that how we are finding bitwise end in a range a of L to R. So this is quite known problem, and it is also in gigs for gigs. Let's say how we can solve this. So we'll take one prefix value. So prefix ij means the number of elements. Prefix ij is, let me write it here in the text format. Prefix ij means number of elements less than equals to I, less than equals to index I, uh, whose jth bit is set, whose jth bit uh, is set. Now, how we can determine this prefix ij? So we can determine prefix ij by prefix I minus one j, and the thing is that the current num size should have the jth bit set. So we can use this symbol, that the jth bit is set in the num size, then we are incrementing the value of prefix I minus j plus 1. I hope you get it. Otherwise, it is the same as the previous element. Okay, so after we got this, that our prefix ij value, then how we can say that the jth bit is set in the range L to R. How we can say that the jth bit is set in the range L to R? So for that, what we will do, we'll check the count of elements, whose bit is set in L to R. Count of elements whose jth bit is set in L to R. Now this will be nothing but prefix of Rj minus prefix of L minus 1j, right? I hope you get it. Now if this element, this thing is equals to all the elements in the range, then we can say that the jth bit is set in the result. So this should be equals to r minus l plus 1. If this is equals to r minus l plus 1, we'll set this bit in the answer result. Otherwise we will not set this bit in the result. So let's jump into the code again. So we are checking that this thing prefix mid plus 1 j, we are using one based indexing here, minus prefix ij is mid minus I plus 1 or not. If this is this condition satisfies, then we are adding setting the jth bit. Okay, I hope you get it. The rest of the part is quite straightforward. I think this problem is quite interesting, and I have to check if there is some solutions which have better time complexity than this. I think this could be solvable using the binary without using the binary search, but I did not get time to think about that solution yet. I will think about that also. If you know the any solution which has lesser time complexity, you can write in the comment section. Also, if you have any doubt in any part of the explanation, uh, you can always ask in the comment section. I will try to reply each and every comment. If you like this video, please like and subscribe and share among your peers. Thank you.